Hi everybody, I'm here to talk about particle motion, and this can be found in your packets. Shoot, I don't know what page, hold on. Page 71 is where we're at on this first key lever. So get your packets out, get ready to take some notes. Our first key lever just involves the relationship between position, velocity, and acceleration. So that's nothing new. We know our stairs for physics are P, V, and A, and every time we go down a step, we take a derivative. So in this first problem, we've got the position of a particle given by this function, sine minus cosine, and we want to try and find the acceleration of the particle at the point when the velocity is first equal to 0. So my position function, is typically denoted as x of t, is the difference between our sine function and our cosine function. So in order to answer this question, I want to eventually find the acceleration at a particular point, and that point is when the velocity is first equal to 0. So in order to do this, I have to first anchor myself in a velocity function. I'm going to go ahead and scribble my quick graphic organizer here. Taking a derivative for sine, that gets me down to a cosine, because the derivative of sine is cosine. Bless you, Buster. Minus, let's see, cosine's derivative is negative sine. So I can do minus negative sine, which would lead me to a positive sine of t right here. So my velocity function is cosine plus sine after I take some derivatives. This problem asks me to uncover when the velocity is first equal to 0. So let's see, that means I'm going to need to set this velocity function equal to 0. I'll move one of those trig functions to the other side, and it looks like I want to know when the cosine is equal to the negative sine, or when negative cosine, perhaps this might be easier, is equal to positive sine. We can put that negative on either side. So basically what this trig equation is asking me to think about is, whoa, sorry, that was ugly. Pretend like that's in the middle there. It's where on my unit circle my cosine and sine have opposite values. That's the way I think about that. So here, this is bothering me. Let me try again. So I'm looking at this circle, and I want to know when sine and cosine have opposite quantities. So one thing that I'm drawn to in terms of my circle is the angle pi over 4, because at pi over 4, 45 degrees, my sine and my cosine have equal values. That's when they're both root 2 over 2. So what I'm going to do is move along my circle over in this direction until I get right over here to that same 45 degree angle, but this time, whoops, I'm at 3 pi over 4, or 135 degrees. The reason I like that so much is because that's a mirror reflection of the 45 degree angle in quadrant 1. So all that means is that my cosine value, my x, is now negative root 2 over 2, but my sine value is still positive root 2 over 2. So I've uncovered a location at 3 pi over 4 where my sine and cosine have opposite signs. One's negative, the other's positive. So that's really helpful. That uncovers when the velocity is first equal to 0. And if I keep reading the problem now, the next thing that they want me to do is evaluate the acceleration function at that time. So acceleration is the derivative of velocity. So I'll take the derivative of that velocity function I had up above. Cosine's derivative is negative sine, and sine's derivative is cosine. So now I'm looking at a function of negative sine of t plus cosine of t. I'll evaluate that at 3 pi over 4 in order to close out on this problem. So that's negative sine of 3 pi over 4 plus cosine of 3 pi over 4. Do some trig. That's negative root 2 over 2 for the sine of 3 pi over 4, plus the cosine of 3 pi over 4 is negative, because we're in quadrant 2, root 2 over 2. Combining like terms, that's negative 2 root 2's over 2, or negative square root of 2. So what is the acceleration the first time the velocity of this function is equal to 0? Well, it's negative square root of 2. All right, so key lever number 2 is just highlighting the difference between displacement and total distance. So something that you should make sure you record in your notes is that anytime you're asked to find the displacement of a particle or a bug or a car or anything like that, that formula is the integral from a to b of a velocity function. Displacement captures our change in position. So an integral is what accomplishes that change. Remember, we've talked about new equals old plus change, and change is always the integral part of that formula. So a change in position, which is the definition of displacement, is defined as the integral over that interval of velocity. Now, different concept to consider is total distance. Total distance is not just a change in position. It's a summation of all of our movement. In total, how many miles did we travel? How many steps did we take, etc. So to find total distance, the formula here requires that we sum up all of our movement, left, right, whatever, and we can indicate that with absolute value bars around that velocity function. That takes my motion and does not care about which direction I'm moving, and instead just sums it all up. So in this problem, the velocity of a particle is given by 6t minus t squared. What's our total distance traveled? Well, that's going to be equal to the integral from 0 to 3 of the absolute value of 6t minus t squared with respect to t. And a lot of times the College Board literally just assesses if you know that formula and if you understand that we need to be putting absolute value bars around our function anytime we've got a total distance question being asked. Most of the time these are on calculator active exams, so I've gone over here and just typed the function into my device, and I can come over here and then do shift plus from 0 to 3. A nice shortcut is to just type abs in your calculator. The calculator is programmed to compute that as absolute value, and then you can pull up your function of x, of course, and put a dx on it, and the answer is 18. Total distance of this particle that the particles traveled over the first 3 seconds or minutes or hours or whatever is 18. Okay, and the last big idea involves speed, specifically uncovering where speed is increasing or decreasing, in this case given a velocity function. So a couple of notes before we dive into this problem. For speed to be increasing, so increasing speed, another way of thinking about that, you'll often hear or see the question asking you to determine when the particle is speeding up. That means that we need velocity and acceleration to have the same sign. So that's a big idea that we need to consider when we're discussing speed being increasing. Along that same line, we can have decreasing speed, which oftentimes they will describe as a particle slowing down. And when that's the scenario that we're interested in, we want to make sure we're checking that velocity and acceleration have opposite signs. One positive, one negative. So in this case, the question states that we have a particle moving along a straight line. The graph of the particle's velocity at time t is shown for times from 0 to m, where j, k, l, and m are just some constants. The graph intersects the horizontal axis at 0, k, and m, and has horizontal tangent lines at j and l. For what values of t is the speed of the particle decreasing? So in this case, for speed of the particle to be decreasing, I'm linking that up with velocity and acceleration having opposite signs. So 2 scenarios are what I'm interested in here. Velocity could be positive, and for speed to be increasing, that would mean I want my acceleration to be negative. So that's one scenario that I could C, that would answer this question. Velocity positive, acceleration negative. Another scenario obviously then would be, well, our velocity could be negative, in which case to have opposite signs, our acceleration would have to be positive. Now it's kind of difficult to address this with a graph of velocity here. Remember, we're looking at velocity. So I'm going to use some stairs too. Let's think. Well, velocity being positive in this first situation, that's not difficult to find. Here I am, I'm trying to highlight that chunk of graph. That's where the velocity is positive. But on that interval, it's hard to know where the acceleration is also negative. So I'm thinking of my stairs. Remember, P, V, A. If acceleration is negative, another way of thinking about that, if I go up a stair, is that the velocity is decreasing. So on just that blue interval that I highlighted on the graph, that of course is where velocity is positive. But if I also want acceleration to be negative, that's going to be where that blue chunk is decreasing as well. So right in here from J to K. That's a J. Sorry, y'all. J to K. And let's not forget to check the other scenario. I could also see decreasing speed if my velocity is negative and my acceleration is positive. So the opposite situation. So here I am with negative velocities under the x-axis. And if acceleration is going to be positive, another way of thinking about that is that velocity is increasing. So on that red window, another place where our speed is decreasing would be between L and M, because we have opposite signs of velocity and acceleration.